Okay, good morning, everyone. So last time we were talking about the partial wave expansion or scattering. And this is just, well, first of all, this applies to spherical potentials, which are very common. For example, the Coulomb potential, the Yukawa potential that we've already worked out the Born approximation for, those are spherical potentials. And so the idea is in those cases, the scattering amplitude only depends on the scattering angle theta. And you can write it as a sum of partial waves, meaning different angular momentum contributions, which looks like this. There's a normalization factor. The angular dependence is in a Legendre polynomial. And then there's a factor that we call f sub L of k, which doesn't depend on the angle. And there are different ways of writing this, but one way is you can write it as e to the I delta L times the sine of delta L divided by k. Okay, and the delta L's are called phase shifts. And so if we can compute those, then we'll know what the scattering amplitude is. And if we know the scattering amplitude, then we can square it to get the differential cross section. So one thing I want to point out is when you do that, when you square this partial wave expansion, you're going to get terms with different L's just because you're squaring it. And so this does have interference between different angular momenta. Or just different L's. Okay, but then last time, the thing we did is we integrated this and we got an answer that looked like the following: 4 pi over k squared, sum over L's, 2L plus 1 times sine squared delta L. Okay, which you can rewrite as just a sum over L's of whatever those numbers are, sigma L's. Okay, and so in the total cross section, the interference between different angular momenta has averaged away. So interference between different L's averages away. And that's just because we're doing an integral over all theta and all phi, but phi doesn't matter. It just gives a factor of 2 pi. But so the total cross section, you can just separate into these different partial waves. So there's an interesting historical fact about partial wave unitarity. The Higgs boson was discovered in 2012, but before it was discovered, so before 2012 discovery of the Higgs boson, one of the arguments that it had to be there, which was not a completely ironclad argument, but it was an argument, is that without it, partial wave unitarity appeared to fail. So one argument for its existence was that, so this wasn't an experimental thing, this was a theoretical thing. If you just calculated the total cross-section sigma for a particular scattering process, namely WW goes to WW, those are W bosons, then the thing that you calculated would not obey partial wave unitarity. In fact, it didn't. Which is a disaster. That means probability is not conserved in some sense without the Higgs boson. So the problem with this argument is all that tells you is that you need to do something to the theory to fix up partial wave unitarity, and it may have been the Higgs boson and it could have been something else. It turns out it was the Higgs boson because we discovered it. So this is a very useful thing. This is all based on the fact that our sine squared delta L, the biggest that can possibly be, is 1. And so that's telling you how big the different partial wave contributions to the cross-section can possibly be, no matter what the potential is or what's going on. Okay, so another way of expressing partial wave unitarity, other than just the total cross-section, is it restricts what your scattering amplitudes can be. So partial wave unitarity restricts for each L what our function FL of K is, or what it can be. Right, so just a reminder, this is our FL of K. It's the thing that gets multiplied by the Legendre polynomial to give you the scattering amplitude. Okay, and so if you just graph the result that we got in terms of the phase shift in the complex plane, so this is going to be the real part of FL of K on this axis, and this is going to be the imaginary part of FL of K. It's a complex number in general. Then you find out it's, so FL of K, reminder, one way of writing it is it's e to the 2I delta L minus 1 over 2IK. And so when you work that out where it can be, it's a circle, but not centered at the origin. It's a circle like that with radius 1 over 2K. And then if you're, say, at this point on the circle, if that's your FL of K, then this angle is 2 times the phase shift. Okay, and so this is known as the unitary circle for FL of K. Okay, and so where you are on the circle tells you something about the scattering. For small phase shifts, for small delta L's, then from the picture, FL of K is near the bottom, which means it's small. If it's near the bottom of the circle, then it has to be near the origin, so it's small. And it's almost purely real. And those are things that happened in the Born approximation. So it doesn't have to be true that the Born approximation is good there, but in the Born approximation, that's what we found. The Born approximation is assuming that the scattering isn't so large that it distorts the wave function near the scattering potential. And remember, when we worked it out, we found a scattering amplitude that was real. And so that's what's going on there. Sort of the opposite of the Born approximation is for maximal K, for maximal FL of K in magnitude, right? So we see that the biggest it can possibly be is about 1 over K. So that's when you're at the top of the circle up here. Okay, and then FL of K is almost pure imaginary. Instead of being almost pure real. So it's at the top of the circle. Okay, and not today, but in a future lecture, we'll explore in more detail what that means. And it means that the nth partial wave is near a resonance. Okay, and your saturate also sine of delta L is near 1, so you're saturating the partial wave unitarity bound. So that's the saturating the bound on your contribution to the total cross-section. Right, so all of that's saying is that if you're near a maximum possible cross-section in a given value of L, then there's some resonant state that is causing it to happen. And that resonant state, if you work out its angular momentum, will have angular momentum L. All right, so far we've been talking very generally about phase shifts. Let's work towards doing an example where we can calculate a phase shift. Okay, so to do this, let's consider potentials that vanish outside of some region. So our V of R, still spherically symmetric, is going to be 0 for R greater than R, but a lot of the things I'm going to say also hold if it's a constant in some region. Okay, but then let's write the form of our scattering cross-section. So it's got this normalization factor, and we're doing a sum over L's. And we put in our 2L plus 1 and our Legendre polynomial. And now I'm going to write here a general function, right, which could be AL of R, some unknown function for R less than or equal to R, big R. And that could be very hard to calculate. In general, it will be. And then there's BL of R for larger R, where you're outside where the potential is. And that is relatively easy because that's a free particle. So when I say easy, we just have to remember that we actually already did this in Physics 660. We just have to remember what we wrote down. And then in general, the problem is going to be to match these at the boundary between the two regions. So match at boundary where little r is big R. Big R is sort of the range of the potential in this case. Okay, so let me remind you from Physics 660 what we wrote down for a free particle in spherical coordinates. And in the notes, this is equation 8.2.21. And so what we wrote down for the radial wave function is it's got two possible parts. There's a constant C sub L, and it's multiplying a spherical Bessel function. And then there's another constant, and that's going to be multiplying a spherical Neumann function, which are scary sounding functions, but really they're just sines and cosines divided by powers of the radius. Okay, so that's the form. And by the way, K is square root of 2me over h bar. And these CL and DLs are unknown coefficients. Okay, and NL of KR is something that didn't occur in the case of a plane wave, but in general, it can occur for scattering problems because it's okay as long as you don't include the origin. This thing blows up at the origin. But if R equals 0 is not included, which is the case if you're describing the wave function way off where the detectors are, then it's a perfectly good function. And in fact, you need those spherical Neumann functions. Okay, so now you can rewrite this a little bit to see how it matches up with what we've learned about scattering. You can rewrite the spherical Bessel functions and spherical Neumann functions in terms of spherical Hankel functions, which we also wrote down in Physics 660. And this is equations 8.2.23 to 8.2.26. And all these things is linear combinations of the spherical Bessel functions. And the spherical Neumann functions. And at large R, what matters to us is they go like exponentials. The H1 function looks like an outgoing wave, and the H2 function looks like an incoming wave. And they're just JL plus NL and JL minus NL. Okay, and so at large R, this behaves, oops, I forgot to divide by R. Actually, there's IKR in the denominator, and this one looks almost the same, except it's an incoming wave. Also divided by IKR. And so those are the forms at large R. So why are we doing this? We're doing this because we want to express the unknown coefficients in terms of phase shifts. And so to do that, we want to match our scattering wave function to the phase shifts. Okay, and so our psi plus of R looks like this again. 1 over 2 pi to the 3 halves. We're going to sum over L's. The usual function there. And now when we plug in that, the spherical Hankel functions, it looks like this. E to the I 2 delta L, e to the I KR, minus e to the minus I KR minus L pi. Right, so the outgoing wave has the phase shift e to the 2I delta L in it. The incoming wave is really coming from the incoming beam, so it doesn't have any phase shift. It doesn't get affected by the potential. And then this is all over 2I KR. Okay, and so now we can take this thing, match it onto this thing here. Actually, I guess I should have called this B. Let me rewrite this. Should have been B. Sorry about that. Because that's the wave function when you're that's the wave function that I decided to call it when you're outside the potential. Okay, so if you match those two things, then you can solve for the coefficients. And if you do that, I'm just going to write the actual function with the coefficients plugged in. BL of R looks like e to the I L pi over 2 divided by 2 times e to the 2I delta L. The incoming spherical Hankel function plus the outgoing spherical Hankel function plus the incoming one. Maybe instead of 1 and 2, we should call them out and in, but 1 and 2 is a standard notation, so we have to stick to that. Okay, and then once you've done that, once you've figured out the coefficients, then you can rewrite it back in terms of the spherical Bessel functions again. So it looks like this. E to the I L pi over 2, e to the I delta L, cosine delta L times the spherical Bessel function minus sine delta L times the spherical Neumann function.
Sorry, Professor.
Yes.
I fell a little bit behind. Is that an N up there after the Hankel fraction 2? JLKR minus INL?
You're talking about this one?
Yes.
Yes, that is an N. Sorry about that.
Okay.
Okay. Okay, so there's our BL of R. And this is valid for all R much, much larger than big R. And the unknowns in it, actually there's only one unknown, and that's the phase shift, delta L. Okay, so now we can write down what the strategy is for solving these type of problems. One is, we've got B sub L in terms of just one thing, and that's the phase shift, and we need to find out what the phase shift is. So the first thing we need to do is solve for the other function. AL, that's the function in the region R less than or equal to big R. Okay, and that is the thing that's usually the hard part. That's difficult, or at least it might be difficult. In the example we're going to do today, in a moment, I'm going to pick my example very carefully so that this part is really easy. But in general, it's the difficult part. And it's going to involve some unknown coefficients, usually. Again, in the example I'm going to pick to do, it won't. Okay, but so it has some unknown coefficients, and now you've got delta L's that are unknown and whatever unknown coefficients are there. And to get rid of the unknown coefficients, as we did in 1D scattering, you match at the places where the two amplitudes agree. So you're going to match AL at capital R to BL at capital R and the first derivatives. So you take the derivatives of those functions and you match those. Okay, and then there will be some equations and some unknowns, and you will solve them to get delta L. And then the third part is super easy. Once you've got the delta L's, then you just plug them in. You plug them into Fk of theta. For example, remember it has this form. Now everything in it is going to be known because we know the phase shift. Okay, and then you can do anything because you've got that. You can square it, you can integrate, or you can find the differential cross-section. You can integrate to get the total cross-section. You can check the optical theorem. You can check partial wave unitarity and all that good stuff. Okay, so that's a general strategy. And so it's best to do an example or two. So we will do the simplest possible example. And the simplest possible example is hard sphere scattering, which we already did classically. And so we're going to do it quantum mechanically and see if we get the same answer. Okay, so this is the quantum mechanical analog of classical scattering of hard spheres, like a ping pong ball off of a bowling ball. So off a bowling ball, I'll just say. Something that's heavy and doesn't move and has a fixed radius. And so the potential that we're going to write down for this is that it's infinity for small radiuses, for small distances, and it's 0 if you're outside where the hard sphere is. So that's a great potential because solving for a wave function in a region with infinite potential is super easy. The solution for r less than r is trivial because it's just 0. And so it's going to be really easy, or relatively easy, I guess, to match that to the wave function outside. Okay, so it's just 0. So in fact, for r greater than or equal to big R, our wave function is going to look like this. We've already written down the form of it. So we've got our usual sum over L, our 2L plus 1, our Legendre polynomial. And then the rest of it we decided was e to the I L pi over 2, e to the I delta L, cosine delta L, JL of KR, minus sine of delta L times the spherical Neumann function. Okay, and so all of this stuff that's what we called A sub L or B sub L before. Okay, and so basically we just need that thing to be continuous, so it needs to match to 0. And so we need B sub L at capital R to equal 0. The wave function is continuous, even if the potential is infinite. The derivative of the wave function is what won't be continuous, but in this case, we don't even care. So all that we have to do, the only way we can make this thing vanish is for this stuff to be 0, because everything else is not 0. And the only way that can happen is if tangent of the phase shift is equal to JL of K big R over NL of K big R. Okay, and that has to be true for each partial wave. For each of L equals 0, 1, 2, etc. If it's L equals 0, you say you're doing S wave scattering. If L equals 1, you say you're doing P wave scattering, etc. Okay, so now we've really solved the problem because these are known functions. You can just look them up, and then you have to solve for tangent delta L by taking the arc tangent. So for S wave, it's especially simple. Let's work out what it is for S wave. Okay, so for S wave, that means L equals 0. We're taking the tangent of the phase shift 0, and the function JL of KR turns out to be sine of KR over KR for L equals 0. And then we're dividing by NL of KR, which is minus cosine KR over KR, just looking up those functions. So that's equal to minus tangent of KR. And so from that, we can conclude that the 0 phase shift is minus K times R. All right, so we've got the phase shift for the L equals 0 partial wave. And so just for fun, we can write down what the radial wave function is for the L equals 0 partial wave. I'm going to forget about constants and just write that it's sine kr over kr cosine delta 0. That's from the J0 part. And then there's plus cosine kr. Oops, that should be little r over kr times sine delta 0. Okay, and then you use a trig identity to realize, aha, that's 1 over kr sine of k times little r minus big R. So we can make a graph of what's going on here. Let me graph not the wave function, because the wave function is getting smaller for larger r. So it's traditional instead to write r times the wave function as a function of radius. And then if it had been no potential, that would have just been this function, just a sine function. And so now what's going on is that if that's the point r, then the wave function is forced to be 0 everywhere inside the hard sphere where you can't go in. And then it just does the sine function. It just gets shifted out, and that's why it's called the phase shift. So the red lines here are if no potential. That's what it would have been if there were no potential. And the blue line is the actual scattered wave function for that spherical wave. Okay, and so it's because it's forced to be 0 where the impenetrable sphere is, it just gets shifted out by a distance k times r. Okay, so that was the L equals 0 partial wave. And now we can do more generally, we can look at what the delta L's are. And so one thing we'd like to do is look at what happens in the low energy or long wavelength limit. So in the low energy or long wavelength limit. So that means k times big R is much, much less than 1. And now you can look up how do those spherical Bessel functions behave in that limit. And here's the answer. This is somewhere in the notes. I didn't actually write down the equation number for this, but it's somewhere. Okay, so the Lth spherical Bessel function behaves for small argument, like the argument to the Lth power over the double factorial function, which looks like this. It's basically a factorial, but you leave out every other term. You leave out all the even terms. So this is 2L plus 1 double factorial. That's just defining what double factorial means. And similarly, the spherical Neumann function behaves like this, minus 1. It's got a double factorial in the numerator, but it's actually only 2L minus 1 double factorial divided by KR to the L plus 1. Okay, so now if we go back up to this expression, we're again going to be setting that to 0. And so we're going to be solving for tangent delta L when we take the ratio. And we're going to get the ratio of JL over NL. Right? So what we've learned is that the tangent of the Lth partial wave phase shift is going to be minus KR to the 2L plus 1 divided by 2L plus 1 double factorial times 2L minus 1 double factorial. Right, so now we can take the arctangent of both sides to solve for that. But the key lesson here is just that as L gets larger, this gets small really, really fast. So this gets very small for larger L for two reasons. One reason is just that we're taking, we agreed to call this thing a small number. We're taking that limit, so we're taking a small number to a positive power. But not only that, but we've got these double factorial functions in the denominator, and they get very large very fast as L increases, as factorials tend to do, right? And so this thing, for even reasonable size k times r, even if k times r isn't that small, these numbers just get irrelevant extremely fast. And so that's a good motivation to only keep the lowest few L's. In fact, often you just keep L equals 0. Okay, so keep only L equals 0 to see what happens. Now we can write down our differential cross-section, which is just sine squared delta 0. So there was a 2L plus 1 factor, but L is 0. So that's just 1 divided by k squared. And so I can write that as sine squared kr over k squared in this example. And so for very small kr, this is approximately kr squared. Sine of very small number is very small number divided by k squared. And so the differential cross-section in the low energy limit is just r squared, where r is the radius of the impenetrable sphere. Okay, and so this is valid for kr much, much less than 1, formally speaking. But actually what we learned up here is that it's even pretty good even for kr of order 1. Okay, so one lesson that we learned from this, by the way, is this could have been a function of theta, the differential cross-section, but if the L equals 0 partial wave is the only one that contributes, then it won't be. It will be isotropic. Okay, so this is isotropic, which means constant in angle. So it was automatically constant in phi because we assumed spherical symmetry, but it's also constant in cosine theta. And on your homework, on the homework set, the last homework set, you were supposed to do another example in the Born approximation, actually, where you're supposed to find out what happens at low energy. And if you do things correctly, you will find out the same thing. It's a very general fact that at low energies, things look isotropic, and differential cross-sections should be isotropic in the low energy limit. Okay, and in this case, if we want the total cross-section, we're just going to be integrating d omega times that differential cross-section. And that is, because it's a constant, just going to give us a factor of 4 pi. And so the total cross-section is 4 pi r squared for this problem. And as a reminder, for the classical version of this, the answer was pi r squared. And so this is actually 4 times the classical result. Okay, so it's a big difference between classical and quantum mechanics. You get 4 times larger cross-section. Okay, so let me write down some of these general facts that this specific example illustrates. General fact valid beyond this example, okay, is for small scattering energies, the phase shift, first of all, is proportional to k to the 2l plus 1. Okay, so we saw that here. It was k to the 2l plus 1, and then for this specific problem, there were some other factors here that won't necessarily be there for other problems, but it's, in general, it's going to be k to the 2l plus 1. Okay, and if you work that out in terms of the energy is like k squared. So this is going to be proportional to the energy to the L plus 1/2 power. And so it's generally true for small e, the L equals 0 partial wave dominates unless there's some good reason why it won't. And so in some cases, you can find out that the L equals 0 partial wave just vanishes completely. There is no scattering whatsoever. So that would be a non-generic feature of a particular problem. But as long as you don't have non-generic features like that, you expect scattering to be mostly S wave. And then as you raise the energy, the P wave will start to be important. And then you raise the energy more, and the D wave will be important, et cetera. Okay, so now what happens if you take the other limit of the high energy limit? Okay, then this expansion is eventually going to fail, even for this case where you have these double factorials in the denominator helping you out. If KR is very large, then the expansion just doesn't even work. Right? And so in that case, many partial waves will contribute. And we're not going to do it for lack of time, but you can show that in this particular example, the total cross-section in the high energy limit behaves like, you might think it's pi r squared because that's the classical, but it actually turns out to be twice that. Okay, so this is true as k goes to infinity, which also means the energy is getting very large. So it's still twice the classical result. And so you can say, well, that's puzzling. Why is that true? And the reason is really because our model for our hard sphere is very artificial. We had this potential that's discontinuous. It jumps all the way from 0 to infinity. And in the real world, there's no such thing. So it's discontinuous at little r equals big R. And so to get the classical result, it turns out you have to do a slightly harder problem. So this is the classical result. So what you need to do is consider a modified potential that's more like what real world scattering from a hard sphere would look like. Here's R. And it's still going to be forbidden in this region. You're still not allowed to be in here. But then outside the sphere, instead of jumping all the way from 0 to infinity, it does something more smooth like that. Okay, and the length scale over which this thing has to be softened in order to get the classical result, that length scale has to be much, much larger than 1 over k, where k is determined by the energy that you're sending in. So this is a smoothed out potential, more realistic in the classical limit. And so you could call this the softened bowling ball. Okay, and one of the reasons we're not going to solve it is now because the potential is more complicated, it's more difficult to solve. But the claim is if you do solve it, then you will get the correct answer for classical scattering. Okay, let's see. So I'm debating whether we should do this other example or not. Let me say no. So let me make some brief remarks in the little time we have remaining about this issue of resonance, and then we'll come back to it in the next lecture. So this is going to be about resonant scattering. So let's write down what the nth partial wave total cross-section looks like. So this is just a reminder. So it involves the sine squared of delta L, and delta L depends on the energy. And so now I'm going to rewrite this in a slightly different way using just a trig identity. Okay, and now instead of writing sine squared delta L, I'm going to write 1 plus cotangent squared delta L in the denominator. Okay, so now usually, meaning, for example, in the Born approximation, that's a very small number, or sorry, that's a very large number. Cotangent squared is a very large number. Tangent squared is a very small number. So you could ask the question, how can you make this cross-section peak? How can you make it be as large as possible? And the answer is the largest it can be is when the cotangent is going to 0 instead of being very large. So, but if it happens that the cotangent of delta L is very small, then the nth partial wave will peak, meaning it will be as large as it can possibly be at the energy that makes the cotangent of delta L small. Okay, and so now the idea is to, let's see what happens if we expand cotangent delta L around that energy. So we're looking at energies close to that energy. And I'm going to call it E sub R. E sub R is the energy that makes cotangent of delta L be small, or be 0. Okay, and so the expansion will have the following form. Okay, I'm doing a Taylor series expansion. There's this term, and then there's the next term, which I'm going to put a minus sign in front of, just because it's a convention. And we're going to take a derivative of cotangent delta L and evaluate that at E equals E sub R. Actually, I don't think I want the minus sign here. Plus order E minus ER squared. Okay, and this is 0 by assumption. And this thing here is just some constant. And it has units of 1 over energy, because the cotangent is dimensionless. And so we're going to call this 2 over gamma, where gamma has units of energy. So before, I claimed that when this happened, it was because there was a resonance, and this gamma is going to turn out to be a property of the resonance that is causing the scattering amplitude to peak, to be as large as it can be at that point. And so next time we'll pick this up and figure out in more detail what this is telling us about the resonance that is causing the cross-section to peak. Okay, so that's next time. I realize I've gone over slightly, but I did want to make a brief announcement, which is because I am getting very soft in my old age, I've decided to make the final exam a take-home and to combine it with the threatened last homework set of the semester. So instead of a homework set and a in-class final, we're going to have a take-home final. It will be out Tuesday, April 20th, and then to maximize your flexibility in how you handle your other things going on during final week, and also in case you happen to be getting sick from getting the vaccine or something. I'm going to make it due Friday, April 30th, which is the latest it can possibly be due, at 5 p.m. with no extensions. So whatever you do, plan your life accordingly so that you will be able to turn it in then. I don't expect that the final should take you 10 days. It will be open book, but closed people, no collaboration or discussion. So you're on your honor not to do that. You can ask me questions, but because this is supposed to be your final, my answers will be restricted to interpreting the question, not giving you hints. Okay? All right, any questions about that? There will be more, I'll be giving out the final hopefully on Tuesday, so you'll get to see what it looks like then. Any questions on today's lecture or about the final? I hope that works out for everybody.
I had a question about the homework.
Okay.
If someone else has questions.
Go ahead.
For number 2, okay, so I was looking at number 1 of the homework, and you talk about that section